Hi everyone. So just a quick review of what we know that Bohr thought about the atom. So he thought the atom had a tiny center that was positive called the nucleus, but he more importantly thought that electrons orbited the nucleus in very specific energy levels depending on how much energy the electron had. So we already have this in our notes, but as we move out away from the nucleus, the electrons have more energy. And his model was called the planetary model because he imagined the electrons orbiting the nucleus just like the planets orbit the sun, in a perfectly circular shape and taking the same exact path every single time. Okay, so how did he come up with that? He studied light that was emitted from atoms after being excited and then moving back to the ground state. So we went over this already in class 2, that the color of light emitted based on which electron is falling from which level to which level, and we get these unique spectral lines for every element. Okay, so now I'm going to jump ahead to de Broglie, who is another scientist that continued to study the behavior of electrons, because the problem with Bohr's equations were that they only worked for hydrogen when there was only a single electron in the atom. Okay, so that's only true for hydrogen, so that doesn't work for all of the other elements that exist that have more than one electron. So up until this point, we said, okay, light is a type of energy, and energy is made up of waves, and waves can also behave like particles, which is something that's kind of crazy. De Broglie said, well, if that's true, then the opposite can be true also. Matter, which is made up of particles, maybe can sometimes behave like a wave. Okay, so what he was able to do was come up with another equation to calculate wavelengths of particles. Particles didn't typically have wavelengths because particles were matter and not waves. Now, de Broglie saying they can act like both. So if we take these two equations, E equals mc squared and E equals hc over lambda, if both are equal to E, then both can be equal to each other. So mc squared is going to be equal to hc over lambda. Now, typically, these problems have us solving for wavelengths, so I'm just going to manipulate it so that wavelength is on the outside by itself. So we have Planck's constant over mass times speed. And I'm not going to write speed as the letter C. I'm going to just write out speed because since we're not talking about waves or anything on the electromagnetic spectrum here, we can't use that 3 times 10 to the positive 8 number. So speed, we're either going to be solving for it or they're going to have to give it to us in the question. All right, so before we move on, things you have to be careful for. Mass has to be in kilograms. So if they give you a mass in any other unit, you have to convert it first. Speed has to be in meters. Okay. Planck's constant we know is in joules per second. And the wavelength, when you solve for it, it's called meters. So if they ask you for the wavelength in any other unit, you'll have to convert it at the end. Okay, so let's do our first example. So I see we're solving for the wavelength in nanometers, so I know right away I'm going to have to convert my answer. And we're talking about an electron, so we're talking about a particle that's acting like a wave. They give me the speed. The units for speed are good. They give me the mass of an electron. Units are grams. Okay, so how do we convert grams to kilograms? There are 1,000 grams in 1 kilogram. So if we take this number and divide it by 1,000, we get 9.11 times 10 to the negative 1. Okay, so now that all my numbers are in the right unit, I can go over here and start solving. So h is Planck's constant. We have mass of the electron, 9.11 times 10 to the negative 31. And we have the speed of the electron. So again, notice that it's not the same as the speed of light because particles do not move as fast as light does. Okay, myself, we get 2.24 times 10 to the negative meters. Okay, and to convert that to nanometers, 1 nanometer is 10 to the negative 9 meters. So I'm dividing by 10 to the negative 9, and I get 2, what would be the wavelength. So if you're calculating wavelength for particles that are acting like waves, you would use this equation instead of the other two we talked about in the beginning of the week. So why is de Broglie so important? Basically, if electrons can act like waves, we can use them inside of an electron microscope. So basically, if we take a magnet, because electrons are going to be attracted to the positive side of a magnet, we can aim or focus the electrons and shoot them at a target. And then we get to see an image that's very, very clear, something that is so small we wouldn't be able to see it in so much detail with just like regular light. Okay, so that's something kind of cool that we can use electrons for. Another thing that's kind of important about de Broglie's idea is that what we thought the atom looked like, or what Bohr thought the atom looked like, is actually going to change, because instead of having these electrons that orbit in perfect circles around the nucleus, we came to the conclusion that electrons do not travel in these perfect circles, but they're found in orbitals instead. And the word orbital is just a region of probability where the electron is most likely to be found. So these two electrons that we drew in this model, they can be found anywhere in this area at any given second. So they don't take the same exact path around the nucleus every single time. It's more of just like a cloud or a region of probability. Okay, so here is the definition of an orbital, which is what we just talked about, that non-perfect circle. And Schrödinger was one of the scientists who contributed to this current idea of what the atom looks like. So that's Schrödinger's cat. So basically, what he said was that if you put a cat in a box with a vial of poison, the cat would live unless he opened up the vial of poison and drank it. So until you open the box, you don't know if the cat is dead or alive, if he opened the poison or not. So you can think of him as being both until you open the box to find out. So that's kind of cool. Heisenberg was another scientist who contributed to our understanding of how atoms behave today, or how their electrons behave. So the uncertainty principle basically just says that electrons are way too tiny and move way too fast for us to be able to know their exact position or speed at the same time. Okay, so just they're too tiny for us to do that. So all of these people together, that's why not one scientist is kind of given credit for the wave mechanical model of the atom. And if you're not sure, you can scroll back into your notes when we talked about the history and take a look at that. Okay, so that's going to be it for today. What I want you guys to do is work on the problems, pages 34 to the sheet packet. That's going to be using the de Broglie equation. Okay, so we did 34 in class the other day. You're going to do the rest of the questions on 34 and 35 for homework. Okay, see you guys tomorrow. Hope you enjoyed your trip.